You spent the hard-earned money, you cleared the bench space, and you finally have that brand new machine sitting in your shop. You take a piece of real, high-alloy American steel, chuck it up, and flip the switch. But instead of a clean, curling chip, you get a high-pitched scream of chatter and a shattered carbide insert. The immediate reaction, the one whispered in every corner of the internet, is to blame the Chinesium, that mythical low-grade metal that supposedly haunts every import tool. But is it really a metallurgical fraud? Or are you just fighting a battle against the laws of physics that your machine was never equipped to win? Today, we are going to stop the name-calling and start a forensic investigation into the molecular and mechanical reality of why these small lathes struggle with the real stuff. The globalization of the industrial base over the last 3 decades has fundamentally reconfigured how we access machine tools. What was once the exclusive domain of professional machine shops, filled with massive, heavy iron from American, German, or Japanese manufacturers, has become accessible to the home hobbyist and the prototyper through a flood of low-cost equipment manufactured in the People's Republic of China. This tectonic shift in manufacturing did not just change the price and the logistics, it created a complex cultural and technical lexicon to explain the massive disparity in performance between a mid-century Monarch or South Bend and a modern import. At the center of this debate is a provocative question. Why can't these modern mini-lathes handle real American steel? This interrogation isn't just about technical specifications. It encapsulates a cultural tension regarding the identity of manufacturing itself. The term Chinesium emerged as a vernacular explanation for catastrophic failures, suggesting a metallurgy that is fundamentally inferior or even fraudulent. However, if we move past the derogatory slang and look at metallurgical engineering, machine dynamics, and tribology, we can separate the shop floor mythology, the fake information, from the physical and chemical reality, the real information. To understand the problem, we first have to address the semantics of Chinesium as a sociolinguistic phenomenon. In the world of hardware failure, the word has become a catch-all diagnosis for any bolt that shears or any lever that snaps unexpectedly. But treating this as a valid material definition is a fundamental technical fallacy. Research into metallurgical databases confirms that there is no such thing as Chinesium. It is not an element, an alloy, or a recognized technical specification. It is a humorous, depreciative slang used to group low-quality products and the imaginary worthless material they are supposedly made of. The persistence of the term stems from a human need to categorize the unknown. When a bolt shears under half its rated torque, or a screwdriver twists as if it were made of lead, the user lacks a spectrograph to analyze the carbon content or crystal microstructure, so they reach for the easiest label available. This is not unlike 19th century terms like pig iron, which described raw or impure stages of processing that eventually stuck in the industrial vocabulary. A massive portion of what is labeled as Chinesium is actually a case of mistaken identity. Many viral examples of these machines crumbling, lathe beds snapping in half, or handles turning to dust, are not made of poor quality steel at all. Instead, they are made of zinc-aluminum alloys, often called zamac or pot metal, which are improperly used in structural applications to save on costs. Inexperienced users see a granular, bright fracture and assume it is bad Chinese steel. The fallacy is attributing the failure to a bad version of steel when the actual error was the manufacturer's choice of material, using zinc where steel was required, or the user's misidentification. Therefore, the claim that Chinese steel crumbles is frequently based on observing materials that aren't even steel. These failures often stem from predictable chemical interactions, like galvanic corrosion or casting porosity, which can happen anywhere in the world if quality control is neglected. The term masks the true root cause, a lack of process control in manufacturing, not a geographic atomic deficiency inherent to China. Contrast this with the myth of real American steel, which suggests that steel produced in the United States possesses a mystical quality that makes it indestructible and effortless to machine. While the American industry maintains high standards, the idea of a sacred metal is often a marketing tool, used to justify premium prices and evoke feelings of patriotism and trust. From a strict metallurgical standpoint, an AISI 1018 steel produced in Ohio and a GB Q235B steel produced in Hebei are functionally indistinguishable if they are manufactured strictly within their respective chemical and thermal specs. The periodic table does not respect national borders. Iron, carbon, and manganese interact the same way in either hemisphere. Furthermore, the idea that American steel is pure while Chinese steel is recycled junk is a gross oversimplification. Modern U.S. steel production relies heavily on electric arc furnaces, EAF, which use nearly 100% recycled scrap. Ironically, because of China's recent industrial surge, they still use a higher proportion of basic oxygen furnaces, BOF, fed by virgin iron ore in certain sectors compared to the U.S. Therefore, the belief that American steel is superior because it comes from pure ore is factually incorrect in many modern contexts. The failure usually lies in the specification. The buyer ordered the cheapest steel possible, not in the technological capacity of the Chinese steel industry. One of the most heated debates involving mini lathes is the use of plastic gears in the headstock transmission. The common narrative is that manufacturers use plastic solely to pinch pennies, and that these gears make the machine incapable of serious work. But this ignores the concept of a mechanical fuse. Engineers design transmission systems to fail in a safe, predictable way. On heavy industrial lathes, there are safety clutches or shear pins to protect the motor and spindle during a crash. Because mini lathes are restricted by space and cost, they don't have these complex clutches. If a beginner crashes the tool into the chuck or miscalculates a cut depth, something has to give. In a scenario with plastic gears, the teeth strip away. The motor spins free, the spindle stops, and the repair cost is a $10 gear with no structural damage. If a user performs a premature upgrade to metal gears and crashes the machine, the kinetic energy has nowhere to go. This often results in a burned-out motor, blown MOSFETs on the control board, or a permanently warped spindle. Modern engineering polymers also offer tribological and acoustic advantages. They are significantly quieter and have self-lubricating properties that cheap, poorly machined metal gears lack. Replacing them indiscriminately often degrades the machine's quality of use by increasing vibration and noise, without providing the imagined gain in robustness. The central claim that mini lathes cannot handle steel is demonstrably false, as thousands of machinists produce high-precision components from stainless steel, tool steel, and even titanium on these small machines. The error lies in confusing the material removal rate, MRR, with the capacity to cut. A 2-ton industrial lathe might take a 5-mm deep cut in a single pass, whereas a 40-kilo mini lathe can only handle 0.25 meters. Both machines handle the steel, but they do so at different scales of time and strategy. However, the most undeniable physical reason these machines struggle is a deficit of mass and damping. Machining generates intense forces, and stability depends on the machine's ability to close the force loop without deformation. A heavy industrial lathe acts as an inertial anchor. A mini lathe weighs approximately 40–50 kilo. Without mass, any unbalanced cutting force moves the entire machine. Furthermore, cast iron has excellent vibration damping due to its flake graphite structure. However, the volume of iron in a mini lathe is minimal. The bed walls are thin and often open at the bottom, reducing torsional rigidity. Finite element analysis, FEA, shows that the weakest points are the joints. Instead of using wide, heavy prismatic ways with precision-adjusted tapered jibs, mini lathes use flat jib strips pressed by point-contact set screws. Under a cutting load, the carriage microscopically lifts or twists. This changes the tool's angle of attack, causing it to dig into the part, which increases the force until the machine flexes and the tool snaps back out. This cycle repeats hundreds of times per second, creating chatter. Harder American steel exacerbates this because it requires higher cutting forces that exceed the machine's static rigidity threshold. To understand the material base of Chinese machines, we must analyze the real technical differences between the ubiquitous Chinese structural steel, Q235, and the American reference, AISI 1018. The yield strength of Q235B is approximately 235 MPa, while AISI 1018 can reach 370 MPa when cold drawn. This means common American steel presents a significantly higher resistance to permanent deformation. Chinese manufacturers often use Q235 as a catch-all material for everything from building structures to machine bolts. The real problem arises when many lathe manufacturers use soft Q235 for parts that should be made of medium carbon steel like AISI 1045. A tool post made of soft Q235 will deform and lose precision far faster than one made of 1045 or 4140, giving rise to the complaint that the metal is like butter. Another factor is steel cleanliness and the control of non-metallic inclusions. Mass-produced steel focused on extreme cost-cutting often suffers from less rigorous deoxidation and refining processes. This results in microscopic particles of oxides, alumina, silicates, and sulfides dispersed throughout the metal. Imagine the steel as a soft cookie dough. High-quality steel is a homogeneous dough. Dirty steel is dough filled with hard chocolate chip inclusions, which are these hard oxides. When a cutting tool hits one of these hard, abrasive oxide inclusions, the edge suffers microchipping. This instantly degrades the surface finish and drastically reduces tool life. Low-cost mills also struggle with batch consistency. An operator might hit a hard spot caused by chemical segregation, leading to tool breakage and machine vibration. There is also the sand problem. Many mini lathes arrive with residues of casting sand trapped in internal cavities like the headstock or the carriage. High-quality foundries use rigorous cleaning methods like vibration and shot blasting, but to cut costs, some manufacturers skip these steps and simply paint over the sand or assemble the machine dirty. During use, vibration and oil flow loosen this sand, which is rich in silica, a potent abrasive. It mixes with the lubricant to create a lapping paste that destroys bearings and gears from the inside out. This validates the perception that the machine self-destructs, though it is due to contamination rather than metal fragility. Furthermore, high-end machines use seasoned cast iron that has aged for months or years to stabilize internal stresses. In mass production, iron is often machined immediately after casting. As these stresses relax over the following months, the bed can warp, losing its straightness and precision, making it impossible to turn a perfect cylinder. Precision. Western machines use materials like mehanite, FC300, with strict graphite control, whereas mini lathes use softer HT200 gray iron. This results in beds that wear faster, forming ridges or valleys, compared to induction-hardened industrial lathes. The inability to cut steel efficiently is also tied to the factory bearings. Most basic mini lathes come with deep groove ball bearings in the spindle. While excellent for radial loads, they are mediocre for axial loads and combined rigidity. When cutting steel, the tool pushes the part both back, radial load, and to the side, axial load. The internal play in ball bearings allows the spindle to move microscopically under these loads. This prevents the formation of a stable chip, resulting in a rough finish and vibration. Upgrading to tapered roller bearings, which can be preloaded to eliminate play and support heavy loads in both directions, is one of the most effective ways to allow these machines to cut steel competently. One of the most prized alloys in the American workshop is 4140 chromoly. Machining 4140 on a mini lathe is a real test of technique because this alloy requires high cutting pressure to initiate chip formation. If your setup isn't rigid, the tool won't bite, it will rub. This causes work hardening, where the surface of the steel becomes harder than the tool itself, making subsequent cuts impossible. To succeed with 4140 or other high alloy steels, you must adjust your parameters to the physical reality of the machine. Industrial parameters will fail here. The real recipe for success involves ditching carbide inserts in favor of high-speed steel, HSS, with cobalt. Carbide requires high speeds and high rigidity. On a flexible mini-lathe, carbide edges chip easily. In contrast, a sharp HSS tool can cut steel with less separation force, which reduces vibration. When sharpening your HSS tools for these lightweight machines, consider increasing the back rake angle to help the chip clear with less resistance. Maintain side relief to ensure the tool body doesn't rub against the rotating part. You must also significantly reduce your cutting speed. While an industrial lathe might run at 300 to 500 SFM, a mini lathe should stay between 50 and 100 SFM to prevent high-frequency resonance. Keep your depth of cut, DOC, shallow, between 0.010 and 0.020, 0.25 to 0.5 mm, to keep forces within the elastic limit of the light bed. Focus on a continuous sharp cut, using extremely sharp hone tools. Mini lathes often lack the power to break a thick chip, so consistent removal is key. Critical but often skipped step for any new owner is the casting sand teardown. Because many machines are assembled dirty to save costs, the first project should not be making chips, but preserving the machine's life. This process involves a complete disassembly of the headstock and carriage. Every internal cavity must be scrubbed of residual molding sand using a stiff brush and solvent. Once the bare iron is exposed and cleaned, the internal's rough cast surfaces should be inspected for porosity. This sealing prevents any missed grains of silica from vibrating loose into the oil bath during operation. Without this step, the sand acts as a silent killer, turning your precision bearings into scrap metal within months. The technical investigation into steel cleanliness reveals that the chocolate chip cookie effect is not just a metaphor, but a measurable, metallurgical reality. In dirty steels, inclusions like aluminum oxide have an extreme hardness. When your tool edge strikes one of these microscopic rocks, it is not cutting. It is being struck by a hammer at high speed. This is why your tool dulls inexplicably after only a few inches of travel. American steels like 1018 or 12L14 are valued not just for their chemistry, but for their cleanliness and predictability. They are refined to ensure that when the tool meets the metal, there are no surprises hidden in the matrix. It is also vital to distinguish between brands, as quality control, QC, varies drastically. While many machines come from the same basic foundries like Sieg or Real Bull in China, their final destination defines their quality. Generic imports sold on volume-based models often have non-existent QC, turning the user into the final inspector. These machines arrive as pre-assembled part kits, requiring a full teardown and rebuild. In contrast, brands like Little Machine Shop, LMS, or Grizzly impose higher specifications, such as better bearings, brushless motors, and solid beds that are not hollowed out under the headstock, allowing for steel cuts that would be impossible on a generic Weaver. The investigation into the Chinesium question reveals that the truth is obscured by operational frustration and cultural bias. Chinesium is a myth, but the lack of rigidity is very real. These machines aren't made of fraudulent materials, they are made of standard iron and steel, but their mass and distribution are optimized for cost and portability, resulting in a critical lack of stiffness. It is the physics of vibration, not the chemistry of the metal, that prevents aggressive cuts on hard American steel. American steel is not magical, but it is valued for its consistency and predictability, which are crucial for precision machining. The chemical analysis of the materials used in these machines often points back to the standard Q235 steel, which is pervasive in Chinese manufacturing. While it serves its purpose for structural components, its yield strength of 235 MPa is significantly lower than the cold-drawn AISI 1018 found in American shops, which stands at approximately 370 MPa. This difference is not due to fake metal, but rather a choice of material grade that prioritizes cost over high-end mechanical performance. When this steel is used for a machine's carriage or tool post, the user experiences a loss of precision because the material itself is closer to its elastic limit under standard machining loads. Furthermore, The HT100 gray iron commonly used in the beds of these mini lathes has a Brinell hardness that can be inconsistent. This leads to accelerated wear in high-pressure areas of the ways, forming the dreaded ridges that destroy accuracy. In contrast, industrial-grade iron like mehanite undergoes strict graphite control to ensure uniform hardness and superior damping. This disparity is a matter of industrial standards and cost, not an inherent inability of Chinese metallurgy to produce better grades. The mechanical setup of the lathe also plays a significant role in the perception of quality. The use of flat gib strips instead of tapered gibs is a cost-saving measure that severely limits the machine's ability to maintain a rigid connection between the carriage and the bed. When the carriage twists under the force of a cut, it creates a regenerative vibration loop, chatter that makes the steel seem impossible to machine. This is often the point where an operator blames the material, when in fact, the machine's geometry has reached its physical threshold. Correcting these issues requires a shift in perspective. A low-cost mini lathe should be viewed as a project, a starting point for a precision machine that the operator must refine. Once the factory contaminants are removed, the bearings upgraded to tapered rollers, and the tool geometries optimized for the machine's low mass, the mini lathe can indeed handle high-alloy American steels with precision. It is the transition from product to project that defines success in the home workshop. As you move forward in your shop, remember that every machine has a personality and a set of limits defined by its mass. If you treat your mini lathe like a delicate precision instrument rather than a blunt industrial force, it will reward you with accuracy that defies its price tag. The key to mastering the real American steel on an import machine is to respect the physics of the setup. Stop trying to move mountains in one pass and start appreciating the finesse of the light cut. The metallurgical truth is that your machine can handle the steel, but you must lead it with the right technique, the right speed, and the right respect for the material's crystalline resistance. In the end, the solution isn't found in alchemy or in searching for a magical origin of steel. It is found in the meticulous application of engineering principles, cleaning, adjusting, and choosing the right tool for the job. The real American steel is waiting on your bench, and your mini lathe, once prepared, is more than capable of shaping it into your next masterpiece.